Hello students, in this lesson we're going to continue on with our work with combinations. In particular, we're going to start by looking at some of those abstract processes, being simplifying and solving, and then we're going to go on and look at a sum of possible combinations, and we're going to link that back to our wonderful Pascal's triangle. We'll start off with looking at some of these abstract processes. Now, if you recall, we looked at how you can simplify using permutations. Now, the process is very similar. Again, we want to be able to cancel out related pieces of information. So let's say we're looking at something like NC2, and I want to simplify. Let's start by writing it out. So what we've got is we've got n factorial on n take 2 factorial and 2 factorial. Now, what we should be able to realize is n factorial and n take 2 factorial should simplify down. So we should be able to look at this n factorial as n multiplied by n take 1 multiplied by n take 2 factorial, meaning that that will continue on over n take 2 factorial and 2 factorial. Now, these two are common. This n take 2 factorial and n take 2 factorial are common. 2 factorial is simply equal to 2, so we can simplify that to n take 1 over 2. If we looked at something a little bit harder, so let's say now we're looking at n plus 2 C3, then we take the same approach. What we've got is n plus 2 factorial, and we've got 3 factorial, and n plus 2 take 3 is n take 1 factorial. So this n plus 2, we can take that down so it includes an n take 1. So we've got n plus 2, we've got n plus 1, we've got n, and then we've got n take 1. So we've just gone down, decreasing by 1 each time until we got to n take 1. Now n take 1 is on the denominator, and we've got a 3 factorial, which is equal to 6. So we've got our cancellation, and we end up with n plus 1, n plus 2 over 6. That's nice and easy. Now we're going to ramp it up. This is a complex scenario. So now we're going to look at an example where we're trying to simplify, where we've got a sum. So let's say we've got NC2 plus NC3. All right. So NC2 is going to be n factorial over 2 factorial, n take 2 factorial, and NC3 is going to be n factorial over 3 factorial and n take 3 factorial. So n factorial in this first fraction will be n take 1, and then n take 2 factorial over 2 and n take 2 factorial. Now we can see that they cancel. And over here we've got n and n take 1 and n take 2, and then finally n take 3 factorial, and it's all over 6 multiplied by n take 3 factorial. And so again, these n take 3 factorials cancel. So we've got n take 1 on 2 plus n take 1, n take 2 on 6. If we want to get a common denominator, we need to multiply this first fraction by 3. So we've got 3n take 1 on 6, and n take 1, n take 2 on 6. And that all comes together to give us 3n take 1, and n take 1, n take 2 on 6. Now, at this stage, we could probably leave it like that. But what I recognize is that we do have a common factor here. We have an n take 1 on both. So if you didn't see that at this stage, that's not a big deal. But because I did see it, I'll take the opportunity to show you. I can also see that there's another common factor here. There's also an n. So I'm going to say that I've got a common factor of n take 1, which means I'm going to take that all the way out in front. And so what we're left with in the first one is simply 3. And in the second one, we have n take 2, and it's all over 6. And so that means we've got n take 1 and n plus 1, because 3 take 2 is 1, on 6. And that's our simplification. Very pretty. All right. We'll look quickly at solving. Now, solving doesn't get much harder. So we're looking to say solve NC2 is equal to 28. So obviously, this solving process includes that process of simplification first. If we can simplify, then we can probably work to isolate our unknown. So NC2 is the same as n factorial, 2 factorial, and n take 2 factorial, and it's equal to 28. We can look at this as n take 1, and n take 2 factorial over 2 multiplied by n take 2 factorial. So we haven't even touched the other side, and we haven't started solving yet. We're just simplifying, and we can cancel this, and now we end up with an n take 1 on 2 is equal to 28. Now we're at a stage where we can rearrange, isolate, and solve. Let's multiply by 2. So we get rid of this divide by 2 then, and we've got n take 1 is equal to 2 times 28, which is 56. Now, I can't solve this yet. I'm going to have to factorize and bring it all over to one side because I can see that it's going to be a quadratic. N squared, take n, and when I subtract this 56, I've got 56 is equal to 0. So now I've got a quadratic that I can factorize. A, C, and B, we've got negative 56 and negative 1. So we're looking for a product that equals 56 that has a difference of 1. So I'm going to say it's 7 times negative 8. 7 plus negative 8, we can see that works. And because this is a monic quadratic, this will just be n plus 7. N take 8 is equal to 0. Which means my solutions are n is equal to negative 7 or n is equal to 8. What's the problem with this fella? I'm hoping you can see that we can't have a negative n when we're looking at combinatorics in this way. So this is not possible. And that means our final answer is n is equal to 8. So a nice solve. It's a good skill. All right. So the last thing we're going to look at in this lesson is this idea of the sum of possible combinations. And so what I mean by this is we're looking at all the possible combinations for a given number. So let's say, start real simple. We've got 2 objects and we want to look at all the possible combinations. And by that I mean that there's no restrictions. We could choose 0, we could choose 1, or we could choose 2. So number of 0 selections, or the number of 1 selection, or the number of 2 selections. So that means we're looking at 2C0, 2C1, and 2C2. And so this is 2 factorial, 2 factorial, 0 factorial, 2 factorial, 1 factorial, 1 factorial, and 2 factorial, 2 factorial, 0 factorial. So this will become 1, and 2, and 1, and it adds up to 4. Now I know that you've seen this pattern before. 1, 2, 1. All right, I'm also going to point out that this is 2 squared. So let's look at 3 objects. And again, we want to look at all possible combinations. And so if we break this down, what we're going to have is we'll have 3C0, 3C1, 3C2, and 3C3. 3C0 will give us 1, 3C1 will give us 3, 3C2 will give us 3, and then 3C3 will give us 1. And so that adds up to give us 8. Now, again, I feel like you'll recognize this pattern, 1, 3, 3, 1. And I'm going to point out that 8 is 2 to the power of 3. Now, I'm not going to waste our time anymore. I'm hoping that you can see these values come directly from Pascal's triangle. So if I redraw that Pascal's triangle, remember that first line is the 0 line, so I'm going to say that that's 2 to the power of 0. The second line, which is 1, 1, is 2 to the power of 1. So 1 plus 1 is 2, 2 to the power of 1. The third line is the one that we just looked at, 1, 2, 1, which is 2 to the power of 2. We then looked at 1, 3, 3, 1. That's 2 to the power of 3. And that next line, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And when we add them all up, 1 plus 4 is 5, plus 5 is 10, plus 6 is 16. 16 is 2 to the power of 4. Now, I hope you recall from last time when we looked at this, we looked at Pascals as combinations. So it would be the same to write this one as 0C0 as 1C0 and 1C1 as 2C0, 2C1, 2C2, and so on. So we can write Pascal's triangle. These values come from those combinations. So we get that symmetry, and we've also got this sum property here. So at the end of this, we're able to say that the sum of combinations starting at r is equal to 0 and going up to n will be equal to 2 to the power of n. So it's a nice simple thing. It gives us a total value that we can start to work at. And so now we can start to look at a new type of question. Now, this new type of question involves a range of possibilities. So let's look at it. Pet shop has 5 puppies for sale. At any time, they will have at least one on show. So at least one means it's got to be 1 or 2 or 3 or 4 or 5. But it can't be 0. It's everything except 0. And we're looking at how many different combinations could they show. And so there's 2 ways now that we can go about this with this new piece of information. We could say that the number of selections is equal to 5C1, 5C2, 5C3, 5C4, and 5C5. So we could say that it's 1, or it's 2, or it's 3, or it's 4, or it's 5. And so that would be 5 plus 10 plus 10 plus 5 plus 1. And so we end up with 31. The other way we can look at this is that the number of selections is all the possibilities subtract 0. And so that means that we can look at it as 2 to the power of 5 and subtract 5C0. Which means that we should get the same outcome. We've got 32, and we're subtracting 5C0, which is 1. So we end up with 31. All right, so it opens up possibilities for questions. We can start looking at big combinations, where logically it makes more sense to deal with the complement, which in this case is what we're looking at. They all add up to 2 to the power of 5, and we're getting rid of the ones that it can't be, which is a much better approach than looking at just the sum of the ones that it can be. Okay, so that concludes the lesson. Hopefully that all makes sense, and thank you for listening.